Okay, thanks, Eric, for the introduction. I'm really happy to be here. It's a new place. I checked if Pascal worked on gravity, and I found out that he suggested this experiment to carry a barometer on the top of a mountain, and in this way show that the atmosphere has a weight. Some people did not believe that. This is quite interesting. I will talk about energy correlators and the way they can be used to constrain gravity. So let's try to see how far we go. And I think it's a nice topic along the lines of using some basic consistency to learn about gravity, and it touches on many things that people discussed recently. And as you all know, if we consider Einstein equations that then by themselves they're not very useful unless you provide some conditions on a stress energy tensor, and this stress energy tensor comes from some consistency conditions on the matter with food, and these things are known as energy conditions. And normally or traditionally, they've been as a way to probe what times we can get, say, in a consistent quantum field theory, because maybe one of the simplest settings of looking at this equation where there is some quantum component is where the stress tensor is stress tensor in some QFT, and we take a that. And this, of course, leads to various theorems in a classical GR, but you might want, say, for this workshop, there is another context in which to think about. So I guess one context is where we really think of energy conditions on a QFT, which enters the Einstein equations. But second context is, of course, where we think of this, say, stress tensor in some CFT, so in some in holography, and then we not use the bulk stress tensor, but as a boundary stress tensor, and then we try to learn something about, say, quantum gravity. And in this case, it is well defined, because if this assumes some semi-classical GR, where we can use the right-hand side of the quantum field theory, in holography, this is a boundary stress tensor. It is well defined, and so we find out some energy conditions, then we can try to learn something about the gravity in the bulk. Now, what are the energy conditions that people came up with for natural errors? Well, the basic thing is that if you take of course, the stress energy tensor is conserved, so we can take a QFT, we can use it to construct, talk about energy. If you take, say, free theory, you'll find, and you look at the stress tensor, you see that it has the structure where you have A dagger, plus A dagger A, plus AA. And so very easy to find states in which the can be both positive and negative. And there are many different ways to argue that in quantum field theory, to take a local stress tensor, or even stress tensor integrated over some compact region, you can find some states where this can be negative. And it's an interesting question how negative it could be, especially, well, there are some results in two-dimensional theories, but in five-dimensional theories, we do not understand it maybe very well. So one simple way to cure this negativity is to consider the integral, and this is what I will be talking about. So this is called the ANEC operator. We can consider some Minkowski states, flight-like coordinates, and consider the integral over dx minus over t minus minus. And basically what happens is when you do that, these two terms go away. And this thing becomes non-negative. Now, what is the status of this statement? Well, in I guess in classical GR literature, people talk about achronal ANAC, which is that here I talk about Minkowski space, but more generally, this is believed to be true whenever you take a geodesic, which is achronal, which means physically it is the fastest geodesic, namely that any 2 points on this geodesic cannot be made time-like. Violation of this, if you take an geodesic on a cylinder, these 2 points are time-like separated. So this is not a achronal configuration, and it appears in many important instructions like reversible wormhole. So this is believed to be true in a unitary QFT. And a nice review, for example, if you're interested, there is this column where you can look at the theorems in classical GR you can prove using achronal ANAC. Now, in unitary QFT in Minkowski space, so here the ANAC is again believed to be to hold here in interacting QFT, not just in free theory. And there are many arguments for that. Depending on your standards of rigor, you can accept them or not. So let me list them, some of them, and what goes in. So well, one argument uses monotonicity of modular Hamiltonian under inclusions, and it was argument by Faulkner et al. So it based on monotonicity of relative entropy, and okay, based on how much. I cannot really comment on all the subtleties that goes into the proof. So let me just mention that it exists, and it's quantum info sort of operator algebra in spirit. But there are other arguments which are sort of more tangible for bootstrap methods, and the one which I want to say a few words about is by Hartman, Jain, and Kundu, who try to prove that this thing holds, starting from just a 4-point correlator in a QFT, and then they use OPE and some kind of unitarity. There are also arguments based on like on bootstrap, on dispersion relations, but all the arguments in a sort of Feynman realm have some and let me comment on the caveat here, which also appears another argument which I will review. And if you want to read about different various Lorentzian approaches to proving ANAC and in QFT, I recommend you read an Appendix A in the paper by Kravchuk, Krichkov, and Chow, who carefully review this argument and various assumptions that are made. And the basic assumption that is made when we here, and it will be interesting if we can make some progress on this or have some ideas during the workshop, is what is known as a light cone OPE. OPE on the potential. So the idea is that you take a pair of pair of operators and you separate it from all other operators, and then you move one operator close to the light cone, then we know that there is a light cone OPE and it has a nice convergence properties. But the crucial step in this argument involves taking, so there are four operators, one operator, say, and you analytically continue it under the cut, meaning you close some light cone. So now the two operators between you're doing the OP are not space-like separated anymore, they're time-like separated, and then you send it to 0, and you take a configuration where, say, Z bar, which are the cross ratios much less than Z, much less than 1, and you assume that light cone OPE holds asymptotically. So that's an assumption that goes in here. This does not follow from any known axioms, and so this is the part of the argument that is not clear here. Now, for me, it seems like, given that there are many arguments which all converge on this thing, it seems like it's an interesting question to ask. What are the consequences? So physically, it is something very natural that ANAC is positive. So we could just well ask, and let me, for the purpose of this talk, I will assume that it is true. And I will simply ask, okay, what can we learn this fact, and pushing it further and further. This would be basically the plan of my talk. So we will start with the properties of, say, one ANAC, then we go to two ANAC, then we go to more ANAC, and then we consider about classical gravity, quantum gravity, etc. Yeah. I guess it is consistent with it, for sure, but how far can you push? Anyone has tried that. So it is, how would you go? I guess if you look at it that way, then ANAC implies a bound on the subleading contributions in this light cone OPE. And so I guess it implies that maybe in some versions that yes, it holds at least for the first term. Because then in principle, when the people talk about this, they assume that there is a symptotic extension, but not sure. But it sounds very reasonable. And I think this light cone OPE on the second sheet, it appears in of the dispersive approaches to CT, so it seems like it's a right thing. No, in principle, it's supposed to hold in any unitary QFT, but all the arguments here, I think there it also doesn't care about the QFT, because its argument effectively sort of done in the UV by taking the light cone limit. Doesn't supposed to matter, but again, then you can ask, well, you have a quantum field theory with some scale, and then you're going to the light cone. Is it really a UV limit, or is it some regular limit? It's not exactly clean, but I think these guys they assume that it's controlled by the UV. And for the other form, I don't think they. Well, they use, I guess they also use some kind of OPE, and in a sense, it's technically more. Yeah. Yeah, I guess it's a little bit like, well, I don't know to what extent this applies, but if you take QCD and you take a regular limit, it's controlled by the non-perturbative hierarchy. You have to make sure that you isolate all the scales that are you never control by the IR, and it seems reasonable. Yeah, 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 yeah. Yes, it's a very interesting inequality, but I don't know of any use of that. So it would be wonderful to use it. Okay, let me then proceed. And the first thing, which is the first thing we will do is we will consider just a one-point function of this guy, and I will make a set of comments and then we can discuss. The first thing we can do is to consider this type of inequality, and at least in a more formal setting, the first example of this type is what's known as a conformal collider bound by Hoffman and Maldacena. And there the idea is that why conformal collider? Because this observables are in collider physics. When you consider a high energy scattering experiment, you measure energy flux at infinity, and the operator that measures the flux on a sphere, in a celestial sphere, is given by this ANEC. For in the Penrose diagram, it looks like this. You have an experiment, stuff comes out, and you measure things here on the celestial sphere. And these are very familiar observables in PCD, very much very actively studied until today. But in the formal setting, you can just ask, does this imply anything? And famously, the Hoffman and Maldacena considered the three-point function of stress tensors, and in high D, it has three tensor structure of free boson, free fermion, and free vector. So this is just a tensor structure computed in a free field theory, and they show that imposing this condition, in fact, implies, and this is the first example of this bound, and this is not obvious otherwise. It does not follow from some more identities, and if you have a four-dimensional CFT, you can express these guys in terms of A and C, the conformal anomaly coefficients, and then there are bounds on A over C. But in the most general case, these are the bounds. Then you can consider psi to be, say, stress tensor plus alpha O, where is it? Yep. No, this is bound. Three bounds, three inequalities, yes. Three inequalities. There are three of these guys. Now there is one combination which is related to CT. So 1 and B plus C2 and F plus C3 and V. And but there are three inequalities. You can translate these guys into A over C, but in general, these are not related to A and C, but they're there. It's only in 4 dimensions they're related to them. Yeah, in 4-dimensional you can, but still even A, yes. There are three numbers that specify this guys, one of them CT and 2 left. And A is yet another choice, but there is a third number, so that's a 3 bound. Yeah. Yeah, so okay, let me comment maybe just in a second. Now the next more sophisticated thing you can do is that you can take the state to be a superposition, say of T and some other operator. You can choose a scalar operator, and then this still should hold. So you have some constraints, alpha 1 and alpha 2. you get some constraints on the various 3-point functions, and this is sometimes called interference effect, because you get off-diagonal 3-point functions. And this was considered by Cordova, Moldavsena, and Turiachi. Basically, you repeat this exercise, and what they got is that slight improvement on, say, this. Here, these guys are larger than 0. But what this guy showed is that you get actually a lower bound, which looks like this, that you sum, say, over all scalar primaries in the theory. Then you take a 3-point function PTO squared, and you get some f of delta, which is also non-negative, and this is the bound. In other words, if you take the stress tensor between t and t, and you get some scalar primary, and it's non-zero. Now this guy could also be 0, depending on delta. It has double zeros. It's the position of double trace iterated, but in general, let's say it's non-zero, then it puts you a bound on NB. It cannot be 0. Then there is this argument based on the why I really like this observable is that because they are very intuitive. You perform an experiment, you act on a vacuum with some operator, it creates a set of excitations, and then these excitations evolve and they can branch, etc. This is a quantum evolution of your state if you evolve with a Hamiltonian. And then you expect that if you have an interacting theory, there will be no angle on the sphere where this flux is 0, because there is no conservation law to prevent energy not to go in some direction. So you would think that interactions should imply that this guy is non for any angle, and this is something special that is violated in free theory indeed. And in free theory, you can think of a free theory. It has higher skin symmetry, and higher skin symmetry protects energy flux at certain angles. And so if you compute this pure boson, you will get that there is an angle where there is no energy flux. And this is easy to understand because in the free theory, if you say act with a stress tensor is a 2-particle state. And so there is no branching in free theory. So therefore, you can just compute it, and you will find the energy flux is 0. And then you can use some argument, which I will not review that, but I will review something maybe more recent and related, to argue that all of the energy correlators are trivial, and then the theory must be trivial. So this is what, in fact, maybe Eric, you can remind me, I don't remember if the claim was that the product would be positive or in the theory where I remember that the condition was that this is the condition. And then for surely just you take one of them, it is violated. Maybe what you're saying that if I take 2 of them, it's also violated, and then it's applied. I just don't remember. And then I think another, so this is I think this is a suggestive argument that but it's not really a theorem. I think this is a clean argument, but also it goes tough, and you have to work here. And then I think David and Eric had an argument, which maybe Eric you can review. I don't remember what was the missing parts in that part, if you had any missing parts. So now, yeah. Yes. So one important thing is that in this setup where you put a naked cry, it commutes with a p nu. therefore, when you study these correlators, it's very convenient to work in a momentum basis. So you pick, and the simplest Q is like Q naught, polarization, and then you explore the field. This is the key point. And this might at first look a little bit strange because this is an operator which is inserted somewhere at scry, but this is a statement that the mu does not commute with this guy. Yes, you sum over scalar primaries O, which appear in the OPE T and T. Yeah. Yeah, I think you can choose any O, and you can choose any superposition. Yeah. So it's principle. You can also consider O's which are not scalar. I'm not sure to what extent it's fully explored, but yeah, I think exactly. Yeah, so I think for each fixed O that you will get some inequality with O1 O, and I don't. Maybe you should choose superposition where you try to turn on all of them. You should check at the paper. But I think if you take one, you will get a weaker inequality, presumably, that in these larger just one of these guys. Yeah, so I guess yeah, for free scalar. So I said that this guy it is equal to 0 because this guy, and well, here all these guys are related to the discursive functional. This F, it has the following shape. So it has zeros, and what happens in free theory, all the operators live on the zeros, and the zeros have dimension. It could be something like 2D plus 2N plus J. Again, an interacting field theory would not happen. Yeah, I think so. It should be, again, okay, since we are now talking about this, let me mention why is this happening? This is the first property which is nice about this object. There is a second property which is that if you act with this guy in the vacuum, you get 0. And well, there are various ways to use it, but actually you might think that vacuum is the eigenstate of the energy flux with a 0 eigenvalue. There is also a experiment using Whiteman function or 50 lighting functions, but this is a true fact. And therefore, whenever you are computing some correlators, you can always promote that you have some O acting on the vacuum, creating a state, and you have some E, you can always promote it to a commutator. E annihilates the vacuum, or here you have, say, O dagger, E annihilates the vacuum. So computing this matrix elements with E using just a correlator or putting commutators in the thing. And these commutators, they tend to have this structure of having zeros at the position of double trace operators. Just because when the operator is double trace, this guy effectively introduces a phase which is 1, and then the commutator is 0. Okay, this is a second thing, and one comment is related to, I think, what Dalimil said, is that these bounds you derive without using ANEX. You can just start with the 4-point function of stress tensor, and this is what was done by in the paper by Tolle and collaborators. They did it in 3D. They just start the 4-point function of stress tensor, use the usual bootstrap, and they derive this bounds. I don't think so. I think it was just the usual bootstrap. You did not. You think it was just conformal bootstrap with thing. But the difference is that when you use this guy, you prove ANEC as operator statement. And what this guy did, they just showed that this is, which is a statement about one matrix element. It's a weaker statement, but for this to prove it, you don't need that. Yeah. 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 Yes. Exactly. Yes. 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 I agree. It's interesting. Numerical bootstrap. It's just a 3D force assembly. What they did was just a 3D force assembly. Okay, let me mention also that you can derive some funny unitarity bounds if you're interested. There is a work by Cordova and Diab, but let me move slowly to gravity. Now, in gravity, what happens? What do we compute? How does the computation go if we do it in gravity? And there, the basic picture is following: is that this guy is dual to. So now, if I assume a holographic CET, this guy is dual to a shock wave, and then studying a matrix element like this, effectively boils down to you take your probe, you propagate through a shock wave, and these guys just measure Shapiro delay, and so it is positive automatically. Now, after you see this, okay, this is a scattering experiment. What is the impact parameter in the scattering experiment? And effectively, because we're inserting the source at the boundary, this is a scattering experiment. It's a scattering at infinite impact parameter. And if well, immediately when you see that, say, well, let's do scattering finite impact parameter. And impose still that this delta V of B is should be, say, positive. And then this leads to this stronger bounds, which is the type sometimes quoted A minus C is 1 over delta gap. Where, I guess. And and recently in the work of Dalimil and collaborators, basically they managed to show that without this picture is correct, and you can derive it using dispersion relations, and morally you will just take a 4-point function, you act on it with some functional, then you see that this and this bound, they come out. But let me also say that this quantity it's a much simpler computation. And, you might suspect that, and then okay, we can work hard and prove it, but looking into the future, it seems like this energy correlator is a nice tool to generate conjectures. You generate some because it suggests something which seems to be correct, and then work hard and derive some better statements. And here, for example, how do you see this sort of thing? You can consider propagation not in a scalar case, but in a case of a stress tensor. And if you propagate a stress tensor through a background, then you can just compute in GR that because now this guy carries polarization, then effectively when you propagate through a shock, you have some transfer metric, which is just the Shapiro delay, which depends on polarization. And then you can compute something like this, and let me just say that if you try to compute this using Witten diagrams, this is a horribly complicated computation. It's an endpoint function of stress tensors. It's very hard, but this computation is actually very easy. And what you get is simply the product of this matrices, which each of the matrix is this shock wave. And then you see that if you take anything, so take any theory of particles of spin less or equal than 2, then you find two things, that unless it is a GR minimally coupled to matter, then H1, H2 do not commute. And second, what you find is that you can arrange this thing such that eventually you get that T can be made negative. So this is another way to see that unless if you just have a theory which is non-minimally coupled and you do not introduce a degree of freedom, then you have trouble in this language. So now this looks strange, that it will not commute. So you can ask, is this true? And as a operator statement. Now, why is it slightly non-obvious statement? It is non-obvious because when you look at the definition of the ANET, it looks like these guys are space-like separated. So in other words, it looks like some integral over dx minus t, say x plus equal to 0, x minus x1, dx minus t x plus equals to 0, x minus tilde, say x2. And so then it looks like these guys, because I put them on the same null plane, the distance between them is just x1 minus x2. So they're space-like separated, so it's better be 0. It should be 0. However, if you look at the computation of this guy in a CFT, you find that, in fact, what we are doing is on a cylinder an integral of this type. So you insert these guys at some null infinity, one of them, the second guy. And when they reach these 2 points, they actually, which are at infinity here in this integral goes from minus infinity to plus infinity, that they become light-like separated. So it has a chance to be poorly defined. It's not exactly obvious that it's correct. But the lesson that you will learn from here is that these observables are sensitive to the Regge limit, and that's what makes them also interesting. And this is the Regge limit because when these guys are here, say, they become slightly separated, and then if you in turn have some other operators inserted, you can show that in fact this is what it is. And then using the non-perturbative bound on the Regge limit, and again assuming these things about the light ray OP on the second sheet, you can show that this is a true thing. And so we get into this picture that if we have a consistent theory of gravity in ADS, then this guy should be positive, this guy should commute. And so if you take Gauss-Bonnet gravity or some random theory which is not minimally coupled to GR, this is violated. So then the question is, okay, well, that's nice, but what else can we learn? And then, okay, as I already said, very similar bounds you can get using this dispersion relation. Yep. Yeah. It's a gravity approximation. It's a gravity approximation, yeah. You assume you just have, say, GR or Gauss-Bonnet. So here I was thinking just Gauss-Bonnet. Not necessarily. Yes, in GR, H is 1. So they commute. In GR, equivalence principle tells you the propagation for the shock does not depend on polarization. It acts on the polarization tensor of this guy. I think that this H is in general, if we think in terms of COP, this is a stress tensor, and this H, positivity of H is the same as positivity of P, right? It acts. It is possible, but if you take the approximation where the bulk is just one minimal coupled jar, you keep this H only in the stress tensor sector, and then you get that it's not positive definite and it's not commutative, and then you need to add extra states. So if you take a string theory, the stringy modes restore. Yeah. Yes, you can calculate H. It will be something delta ij, and then plus Gauss-Bonnet, and I and j minus delta ij times a number which makes it traceless, where I and nj it's the position of this guy on the sphere. Yes, exactly. It's exactly. So again, here, if you do this, this is a computation of this experiment at large impact parameters. You can do this experiment at small impact parameters, then you get something like bi bj times say b to the fourth. And so you can, it depends on the, but it's the same type of thing. Yeah. H changes, but again, it will violate commutativity and it will make it negative. Yeah. Yes, it does. It does. In fact, H in string theory is no, because if you take the propagation of a string through a shockwave, it's a solvable background. So H acts in a one string Hilbert space. You can take it, you can compute the commutator, you get 0. What happens is that you get a contribution from Gauss-Bonnet, but then you get a contribution from stringy mode and exactly the same. Yes, it becomes infinite by infinite metric. However, to every order in alpha prime, it only couples to one level. So to every order in alpha prime, it's a finite by finite. It's actually an interesting question if it's always true in PhD, I don't know. But if you expand on the delta gap, so this guy is finite dimensional match. It's string theory, it is the case. Yeah. Yes, exactly. Yes. Yeah. Yes, exactly. That's yes. Yeah. So now you will have here, say T. Right? And now you can again ask if the commutator is 0. Okay, now I want to make a comment, which is so first there is an interesting property that the sensitive to Regge limit, and this I will discuss in a little bit when I will discuss corrections, stringy and quantum gravity correction to this quantity. But before we go, I would like to make a little comment. It's based on the Julian Clement-Piron and Alex Bilan. The question we would like to ask now, okay, here what I said so far, at the level the 2-point functions, at the level 1-point functions, we have some bootstrap method because underlying of this is a 3 or 4-point functions to analyze it. Can we learn something the higher point function? So what about multiple ANet? So I just want to make a little comment. So one of the often quoted statements in the subject is with HPPS, and HPPS is a statement. It's referred to the work by Hemskerk, Penidonis, Polchinski, and Sully, which says that if you have large n plus large gap, you have semi-classical gravity. Now the curious thing is that this is a bootstrap statement, but we need to explain what do we mean by this thing, right? To make a bootstrap. And with large gap, it's usually well explained that in the large n theory, let's say you have single trace and double trace operators, and dimension of higher spin single traces, and it has to be very large, which is the same as to say the stringy modes are very heavy. But what exactly do we mean by this statement? It was, of course, this emerged in the context of thinking about gauge theories. And if you have large n gauge theory, you have an argument of Fock, where you take a bunch of single trace operators, and then you can expand at large n, and large n is the same as what we call a CT, the 2-point function of the tensor. Then you can have an expansion in terms of the topological expansion in terms of diagram, and you have some function. Now, the question is, how do we know that? Is there a bootstrap argument for that? Let me ask this question, because, okay, if we believe this is true, maybe we first want to understand what is the structure of large CT expansion in a general CT. And let's remind you that CT is defined as a 2-point function of the tensor. And so as a bootstrap person, I would say that large n is meant that the 2-point function of the tensor is. So this is a really clean bootstrap way of stating that. But then if I just tell you this, and we don't have a gauge theory underlying the CT, we don't really know a statement like that. Not to prove that. And so the question is, is there something that we can prove? And physically, why something like this is tricky to prove is because it's clear that if you say model a strongly coupled QT and couple it to gravity, is not a string theory, then this is not a bit different from the string theory examples where all couplings are suppressed by CT. Strongly coupled QT, there are a set of couplings, nothing to do with gnu. And what you might want to prove is that maybe this implies at least weakly coupled gravitational sector, which means something different, that we take range of T and we expand it in terms of gravitational loops. And so CT must have this expansion. Again, I don't think in Bootstrap we have proven that. So when we say this HPTF and we say large N, there is missing bit. Let's try to simplify it even further and ask, can we prove something like this? The connected guy, I take a connected endpoint function, that the connected leading term should be scale SCT. Now, okay, this is just physically what it means is that, let's say you take a tree-level gravity and you compute it at the leading diagram. It will, in classical gravity, it will scale like CT. Then you start computing some loops using matter. It should not violate this scaling. Yeah. So this is yes. So this is a statement that if you have a semi-classical gravitational theory. So this is a prediction of the right-hand side. Semi-classical gravity, this is G Newton. You just compute and you get, yeah. 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 Let's discuss that. I think we can also discuss what comes next, and it's interesting, but let's focus on what you suggest. The leading T. Yes, exactly. 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 There is a term which grows like CT, but we want to show that nothing grows faster than. And a simple comment is that not quite that, and again, physically it's clear why, but let me just quickly show that if I take these T's, I turn them into ANX, then this has to be true. And the argument is really trivial, but let me just explain it. So let's try to see if this is true or not. Even simpler, if I take this connected guy and turn it into X. So the question is, I integrate this guy and I ask if this is a CT. And then you see that indeed it has to be, and here I will use another little piece. So first, I told you that these guys commute with p mu, but also, in fact, you can integrate it on a sphere to generate a Hamiltonian. Because it's made out of tensor, so you integrate it over a sphere, you get a Hamiltonian. Therefore, if you start with a stress tensor, if you start with this guy, and you say integrate one of these guys, you just get back Q naught, which is the energy of the state, if I work in a momentum eigenbasis, and get a interrelator with less points. So this is not momentum conservation board identity. And second thing that you use is that all these guys non-negative. And the third, by definition, we know that TT is like CT. And now you see that if imagine that any of these guys, which notice that because this is annihilate the vacuum, it only depends on the fully connected correlator. If you take a disconnected piece, it is 0. It does not contribute to this. So it does probe this guy. And imagine it violates this. Well, then, because it is positive, I can integrate all these stress tensors to go back, all these energy correlators to get back to CT, and it will still scale larger than CT because it cannot cancel against anything. So therefore, it is clear that guy is effectively bounded by whatever Q naught divided by the volume of the sphere times n times CT, and therefore we see that indeed this is the right scaling. Now, okay, if we believe in this HTTPS, the conjecture would go that not only this is true, but this is also true, but this is for the bootstrap for the endpoint function. This is for the bootstrappers of the future. It's too hard, but this thing is very easy to prove, and it just follows from the fact that these guys cannot cancel with it, and the fact that they satisfy this word identity. You can integrate them all out and bound it in terms of two-point function, which is color space. Yes, the TTT gives. So you get well, it tells that the connected guy should at most scales like CT. A priori, it's not obvious because CT, if you remember, is NB plus NF plus NV with some numbers. And a priori, you can cook up a combination where this guy is fixed, but you make this, say, large plus and this large minus. But from the ANEC, we already know this cannot happen. And this is just generalization to endpoint. So you cannot hook up a constellation, and so they all should scale like CT. And the simplest physical example of this type is imagine you have something like people discuss in the context of species bound, where you take a GR and you couple it with a bunch of scalars. Well, then you see what happens is that if you have a GR, the answer is 1. This is what this guy does to leading order. And then if you start computing the one loop correction due to these guys, you have diagrams like this. And well, this diagram has an F in it. It has CT in it. And it has some function f of z, f of the angle. And plus you have some other diagram. So now you see the argument, how does it go? We know that this guy satisfies word identity, which here implies that this function should integrate to 0 upon integrating on the sphere. Therefore, it has to be negative somewhere. Therefore, if I see it somewhere, this whole thing should be positive at this point. Therefore, NF should be less or equal than CT. This is the quick argument. Now you can complain about this argument. For example, you could say, could it be that these diagrams actually cancel this guy? And you can argue that it couldn't happen. That's the first comment I want to make. Second is that there was again a paper by Dalinel and friends. They derived some similar story, but I think that the problem with this computation is that if you take NF of order CT, then in fact the perturbation theory here breaks down, and you have to resum all the bubbles. There are chains of bubbles similar to what Shota and friends have been computing. And then the statement is that, okay, you have to resum these bubbles, but again, it's clear from the structure of these contributions to the energy correlators that this cannot cancel. So there will be bound of this type. Now, the precise bound has not been derived. And I guess, okay, the prediction from this argument is that if we do dispersion relations and dispersive bounds with this resummed bubble chains, we still get some kind of sticky path. Yeah. 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 The problem is that you do not have this. But notice that you have to locally, this guy has to be positive. Not just H is positive, but locally, when you're integrating them on the cylinder, it's some correlator of local operator, and it's not positive. Not run the argument. It's really crucial that locally on the sphere, this is negative. That was the key point. And also a second comment, of course, here you can instead of teach it would be lines of this HPT slide with all the connected guys are spheres like CT. But when you go from this to this guy, in principle, there are terms which are killed by the commutator. So you can go from here to here, obviously, but but knowing this does not imply that the connected guys. This is a stronger statement. I don't know if it's true, but at least this statement is true, and also it's closely related. So I think what people call species bound, and it's clear that here in ADS you can make it very precise. Yeah. Yeah. So here what happens is that perturbation theory brings what in the just need to resum the bubble. You will have to renormalize CT, but also there will be a more complicated structure. But yes, one has to renormalize CT. It gets self-yeah. So this computation has to be done properly, and it has not been done. Exactly, yes. So if you don't have these bubbles, the other guys will be further suppressed. So you can just focus on these guys with bubble change here and bubble change here, and renormalize CT. Uh-huh. Yeah. Well, not in M theory, not in M theory. In theory, in fact, this is not correct, right? In M theory and ABGM, there are other powers of the field that relate exactly to it. Yeah. Okay, yes. Yeah. Right, you're saying that if you prove this, then you're just copying everything into. Yeah, it's a bit tricky because PT always non-minimal coupling, right? But otherwise, yeah. Yes, if we accept that, right? Exactly, yeah. Yeah. No, I agree. It's yeah, it's a nice iteration. So yeah, basically here, what I'm saying is that one does, it seems like this argument suggests that if one repeat this computation, which Dalinov and friends did with some bubble chains, one should still get a bound of the set. Next, if I still have time. Perfect. So I would like to discuss quantum gravity corrections to this energy correlators and why why this is interesting. The key, there is one thing you might be puzzled by. Let's say you read the paper by Hoffman and Maldacena. If you paper, you find the following thing, that they don't write it, but then if you look at the other papers, if you start with this 4-point function from which you can compute 2-point energy later, and you look at the tree-level GR, let me normalize it to 1, and then you look at the first finger correction, it looks like this. Times in Mellin space, it's just a constant. Oh, then you look at their paper, they compute this guy, and it looks 1 plus 6t squared over lambda, 1 minus, let me write. This theta is just the angle between detectors. And it's here. And the puzzling thing is here that if you look at this power, here it is 3/2, and this is 1 over lambda. In other words, there is an extra square root lambda here. Now, what is the physics of this guy? This is related precisely to this fact that these observables, it's not really, I mean, in supergravity, it's good to think about them as a propagation through the shock wave, but as soon as you do a step to the side, it's not correct anymore. If you think of them as a really scattering experiment, because what happens here is that you have this correlation function, and when you compute the energy correlator, you probe the radial limit. And what happens is that if you take this correction, the first finger correction, and you plug it into the computation of energy correlation, it's just infinite. What happens is that effectively, why is it infinite? Because if you expand in lambda, all know that the amplitudes behaves as say 1 over lambda to the 3/2, but in the string theory, you will get times S alpha prime T. So schematically, that the radial limit in the full string theory is softer than the one that's expanded. And this softness exactly what makes this thing is actually finite. But when you do the integral over energies, which captures this guy, then you get an extra power stupid lambda, which turns the form into factor. And so let's call this property of the strongly coupled energy correlators that I call it enhancement property. The same story happens, and this was computed already. This was already computed by Hoffman and Maldacena. How did they do it? Well, they went to shock wave as metric, which is known as finite alpha prime, to do the computation, and in this way, then they get this number. Now the question I would like to discuss next: what about 1 over CT or quantum gravity correction? Just one loop in gravity. You can ask, okay, well, let me take one loop sugra, which has been studied in the last 5 years a lot. What is the correction here? This is the problem I would like to discuss next. And again, if you just take one loop supergravity, you plug it into the energy correlator, you get infinity. Infinity again comes from the fact that, as you know, in perturbative gravity, you have amplitudes which behave in already limit, let's say G Newton S, then you get G Newton S squared plus dot dot dot. So it behaves in the already limit worse and worse with every order in G Newton. And again, if you want to make this computation, you first have to go to finite CT, then perform the computation, and then do the expansion. So in other words, what I'm saying is simply that computing this observable is the red limit of the theory, and the red is not with the perturbative expansion of some stuff. It does. Stringy perturbation theory does not commute for gravitational perturbation. So let me then do that computation now. Yeah. What was the second option? Yeah, so it's a loop correction. It's a one loop in gravity, and it's a loop correction to one. Taken to infinity, yeah. We'll see that it's tricky in some cases, but yeah, formally take lambda infinity, just do gravity. No, it's a gravity in ADS. Take gravity in ADS and so lambda is our ADS. And so when you take lambda to infinity, in this string scale is very small. Now here, the important point is that let's take lambda to infinity. So we have ADS phi versus phi, and we have just gravity in it. And then you can one loop in gravity and try to compute what is the leading direction to that. Solve. To make this connection with high energy scattering a little bit more direct, let me draw a series of. And by the way, let me start with a simple comment is that there is a very nice intuitive understanding is it one, because if you are a collider person, then you have a with gluon and at strong coupling, they branch very easily. Many particles, and they cover the sphere, so you have a homogeneous distribution on the sphere, and this physical intuition immediately makes you make another conjecture, which in fact the mechanism to produce this multi-particle state. There are two mechanisms. One is the dynamics, at strong coupling things branch, but there is a second intuitive mechanism to generate many particles, which take the state to be heavy in a CFT. Therefore, in general, immediately this picture implies, this is a side comment, that if you take, the conjecture is that if you take delta heavy to infinity in any CFT, that this correlator of multiple stress tensors is just equals to 1 plus some corrections by delta heavy minus alpha. This is related to ETH, but it's not ETH. But this is something that is very intuitive, and an all-known example is true. Okay, so let's start with the picture that we have. We have a flat space. We have a pair of stress tensors. They are integrated along scry, and you have an in state and out state. So it's a Schwinger-Keldysh-like contour, because we're computing expectation value. So we take an operator, we evolve it forward, we insert guys, and we evolve backward in time. Now, first we can notice that if you have a CFT, there is an exact symmetry where you can take an operator which acts on a vacuum and translate it one repatch forward. So in fact, this is equal up to a phase to this configuration. Now, one way to understand this is that simply because you can check that when operator acts on a vacuum and it's translated by one repatch forward, all the cross ratios stay intact. It's exact symmetry of the theory. Then, well, if we now put these guys close to here, and these guys close to here, and these guys here. This is precisely the bulk scattering experiment. You know, we take, let me draw it flat. We have one guy on and the second guy. This is when we discuss bulk scattering. This is what we do. And well, this is on the boundary, and finally you can inflate it. You put some holographic air, and it becomes really scattering in ADS. So it is this guy and that guy. And here there is some impact parameter, which lives in hyperbolic space, and there is some energy. So this shows you immediately that, yes, this energy correlator will be sensitive to high energy scattering. But let me write a precise formula that you can derive. Yeah. Yeah, here I'm always taking the plane waves, evolve them a bit in Euclidean, and nothing changed. So in principle, they can be made normalizable, but in practice, you always can take some wave packets and send their width to 0 to 0. Yeah. Where was this? It was 6. I'm sorry, it was 6. 1 minus 6z plus. It was 6. No Newton's constant. Yeah, sorry. Yes. There were two remarkable facts about this polynomial. Well, not remarkable, but I told you that you have to satisfy word identities, and you can check that if you integrated z1 with 1 or with z, it gives you 0. This is how you can fix this polynomial up to its own. Okay, now I will write a formula and just make a bunch of comments, and we can discuss. The statement is, so let me take now 2-point correlator in some state, which is generated by a local accelerator acting on a vacuum. And I assume that my theory is a holographic theory, so it's a minimally coupled GR to some matter. It could be GR on the ADS 5 times something. It could be different dimensions and different manifolds, but the coupling is minimal. Let me assume that this is some particle minimally coupled to this guy. And then the claim is that you get the following. And I'm interested in the contribution of the Regge limit, because this is where this contribution comes from. This is where we need to regulate. Result is let me explain everything. And what is U? U is related to impact parameter. This impact parameter L, and it is between 0 and 1. L goes between 0 and infinity, and U between 0 and 1. This kernel, this I delta, this is the phase shift which corresponds to the scattering. This is characterized by some phase. The kernel is kinetical and is fixed. It's an explicit function, explicitly known, and it satisfies word identities. So the word identities is just the fact that you can turn this P into momentum generator and you should get the right result. And this translates to the fact that you integrate dz 0, 1, z1 minus z, z minus 4 over 2, 1 for z times k equals to 0. So basically what I'm saying is that for any phase shift, this formula satisfies word identity. Has a nice feature. And finally, what are these brackets? They are defined as a third moment of the integral over energy. Now, why third? This number 3, you can think of this in general in the language of light iterators. The number there will be G1 plus G2 minus 1. Stress tensor out of which we build the detector is spin 2. So you get 2 plus 2 minus 1. And delta is a phase shift. And here, the lower scale doesn't matter. Nothing will depend on it because we're only focusing on the things which come from the UV, from the high energy state. And now you can see what happens. So what happens is that you can ask, what is this delta in gravitational theory? In the gravitational theory, it's given by G Newton S times the propagator in the hyperbolic space. And now you see what happens, because let me try to compute this integral. We have the S over S cubed, 1 minus e to the I G Newton S times some function. And here we need to take a real part. So the first guy, linear in G Newton, is exactly imaginary if we expand this guy. But the second term naively produces for you G Newton square S square phi square. And now you see indeed this integral diverges on the UV. And this is a statement that if you just take a one loop result in gravity, which is G Newton square S square pi square, and you plug it with the computation of energy correlator, you get infinity. This is what I was saying. But now you know that at finite G Newton, this guy exponentiates, so it iconalizes, and then the integral is finite now. And if you do the integral, you get effectively log G Newton times G Newton square, G square with some coefficient. Therefore, the prediction is that the first quantum gravity correction is 1 plus log Ct over Ct times some function. Now, this is several comments, and the reason is, first of all, it looks like we did the computation in some sense at G Newton, which is risky. So how exactly this was done? And this is an important question. But let me first comment on a few other simpler physical aspects of this. Yeah. Yeah. Exactly. Yes. Exactly. Yes. Yes. It's important. You have to know which path you went, and that's why this is only symmetry if this guy or that guy acts on a vacuum. If these guys are somewhere in the middle of the correlator, you see that you go under the branch cut, and you do not come back to yourself. So that's so easy. It's a Mandelstam S for scattering in the bulk. Haven't thought of this analogy, but to me, this yes, A theorem also computes the third moment. right? It's ds over q. And here, I guess the only thing, I don't know, but here the scattering is in the bulk. That's what is important. But otherwise, indeed, whatever we're computing a third moment in energy, whatever theory is, stringy or gravitational. Yes, it's because in principle, this guy, that's a complicated thing, which we hard to compute. And we know but what I'm saying is that the term which diverges is enhanced by this extra factor, which is log CT, and it is more universal. It comes from this phase shift in the bulk, and if you start looking at terms of order g Newton square, they will receive further corrections which are harder to control. It's because it's more universal and it's more simple. Yeah. Not for the stress tensor. So for the stress tensors, if you look in perturbation theory, it's 1 plus 1 over CT plus. It's just to compute this guy, you need to first sum. That's what we did. Then integrate and then expand. No, it doesn't violate. But I think that, as you will see, there is something interesting here. I will now list it, say a few words, make the comments, and then we'll. First, we computed this in pure GR, and take say ADS4, 53, and you get log 6 over CT, 1 minus 8/5 Z log 4Z plus 6. It's a very simple result, so I'll write it. With the precise coefficient. And the important thing here is that you see that there is this non-analyticity. It has log Z. And this non-analyticity is related precisely to the fact that this is a scattering at large impact parameter. In fact, you can ask what happens if you take this propagator, say, and plug into the formula which I wrote for the energy correlator. So you take just list some comments. But what happens if you take the propagator and integrate it against this kernel K? What you get is roughly you get F, which is a scale block, which appears in a light B, plus something which is analytic. So this is just to say that this is make a connection with the light field E, that the celestial blocks, they are non-analytic in E. They have this V to some delta here. And this non-analyticity stems from the fact that it describes this large impact parameter physics and idea. And you can make it a little bit more precise. If you apply the Reggie theory to the phase shift, you do get the correct light field structure. Okay, I should really finish. So I will say another comment. If you do now, what if you do, and okay, you get formulas for any ADS, but what happens for ADS5 process 5? So what happens is that if you have a high energy scattering of gravitons, if you have an internal manifold here, then you start mixing with the KK mode. And so to this computation, you have to rediagonalize shift, and you can do that and give it for ADS5 process 5 using the result of the loop computation and the gravity, and you get again some result. And it has some a universal, if you wish, it has some universal log ZPs, like here, which always come from the fact that the very large parameters, you have gravity, but then you have corrections of this type, which are sensitive to the KK modes. Now, another interesting thing that happens, and I'll try to finish, is that if you look at this kernel, at small impact parameters, it behaves like u to the d minus 2. And if you look at the phase shift, it behaves like u to the d minus 3. So overall, if you have an integral k t squared, you have whatever 2d, you should have d minus 4 minus d here. And therefore, in d larger than 4, you have a divergence at small impact parameter. But as I try to motivate several times already, that there are no really divergences in this business because energy correlators are finite. So divergences, they only mean extra enhancement. The extra enhancement terms which we should regulate. And this divergence at small impact parameters, for example, in n equals 4 super Young-Mills, we expect it to be regularized by string effects. And in fact, you can compute it. That's what we also did. You use the Regge theory for the phase shift. You estimate the stringy corrections, and you get that, say, if you take EE in n equals 4, you expect something like 1. And then you get terms like this. Delta gap some power over CT, 1 minus 6g, say, plus 6g squared, plus this log CT over CT times this thing that I computed. And again, the fact that this is a polynomial in Z, this is related to small impact parameter physics. The fact that it has this delta gap here is that unitarization is due to string effects. And why is that? Let me make it. Don't remember what the power here, but let's say square. Why is it a bit interesting? It's a bit interesting is that it's a version of the argument we had for the species bound. Naively, we start with large CT and large gap, and you would think, well, these corrections to 1 are always irrelevant. We will never get anything interesting from them. But here, the point is that because of this Regge enhancement, you get this 1 over CT suppressed, but delta gap enhanced. Now, if you naively impose that this guy has to be positive, you get this bound of the type CT. And so this suggests that if we try to repeat the bootstrap example, the one that's done on the by Tolia, and we add on top this condition, which was not imposed, it might lead to interesting constraints. Okay, it might not, but at least naively from this picture that we get the enhancement stringy by CT, and so we get the string scale is bounded by the Planck scale from this reason. Would be interesting to do it explicitly, to do the bootstrap for this thing and see if it's true or not. But I think so far in the bootstrap analysis, this bound is not important, and it does not follow from other bounds. The last comment to finish is that I said that this is a finite G Newton, in a sense, finite G Newton computation. So how come we managed to do it? The reason is that it's a finite G Newton in a very mild way, which, to make it precise, it's like this. Let's imagine you have the 3-level phase shift, which G Newton, P, L. Now, and here there is energy S. Now, physically, we expect, let me take S and L such that this delta tree is of order epsilon, and epsilon can be very, very small, but fixed number. So it could be 10 to the minus 100. This means that the interaction between your two gravitational objects is very, very weak. Is very, very weak. No matter how huge is S, you separate them so far that the interaction is weak. Now, what happens in the full quantum theory? A priori, we don't know. And to make sense of this computation, we used what we can call the gravitational clustering, which is the following statement: that imagine now you take the full phase shift in a non-perturbative theory, and you sit in the regime in S in L, where the tree-level interaction is tiny. What we want to see is that whenever this guy is tiny, the full phase shift can be bounded by some energy-independent number, some delta tree. What does it mean physically? It means the following. Imagine you do experiment at very high energy. When we do experiments at high energies, the objects which scatter, they can grow with energy. The famous example is the transverse spreading of strings, where one string sees another string as having effective size as a log S. So what could happen in principle? How do you violate this? You go to huge energies and you go to huge impact parameters. But imagine your theory has objects whose size grows with energy as S to some power. Maybe it's 1 over d-, I don't know. So now, if this happens, then you can violate this bound. So this gravitational clustering, it's an assumption that we do not have objects in our theory for which, when the tree level looks tiny, it would break down completely. The perturbation theory would break down because we have this huge object of huge size, and it becomes a very, very IR. For example, one example, a black hole. But having black holes is pretty much very consistent with that. So black holes do not violate that. It would be some exotic object. So the whole computation is only possible, and it was the assumption because finite G Newton, because we assumed this gravitational clustering, which maps to the statement that we do not have exotic objects, which are not like strings. And okay, how to prove this, I don't know, but this is essentially what goes. If you want to derive a Froissart-like bound for gravity, this is when you need to assume. And I don't know of a better way. Well, one way maybe is to go through ADS, but again, it seems like what we get from by taking the limit of ADS is consistent with that. Physically, I think that's the assumption that our gravitational theories have a bound on how quickly sizes of the object can grow with energy. And this is what makes it goes into this computation. Yeah. Yeah. Yeah, so in general, this guy depends on the dimensionality of the bulk, because as I told you that here, what happens here is that K has the dimensionality d minus 2 of the boundary. T has dimensionality U, dimensionality of the bulk minus 4. And then you have the divergence du, u to some power d minus d, whatever. And then this divergence is it becomes the power of delta from a string unitarization. So in principle, here you have a power that depends on d minus d type of thing. And For example, in ADS5, in ADS5 CFT4, this would be, this guy will not be there, but in ADS5 process 5, this guy is there. And I don't know what we expect. Because okay, we are in ADS, and I'm not sure there is an argument which leads to an expectation. Maybe if you say that the string scale should be less than Planck scale, if this is a bound, yeah, maybe it would be good to translate this. Because in principle, we have RADS, and so the bound would be L string from RADS. Let's say. It could be that this is a weak bound, right? It could be that this is a weaker bound, but maybe this is a stronger bound. Yeah. Yeah. So I think it's to make. You expect this to be 1. You expect that this guy goes to, yeah, here I put C0 because you expect that this guys to delta 3 plus order epsilon correction, but they're small, and so it's, yeah. And you can, for example, plug this formula the black hole production. You put into the formula black hole production because again you expect it to be there, and then you get some prediction 1 over 50 cubed log v d minus 1. Now, the key to this whole business was that I can isolate this Regge limit from the rest, because the rest physics, which I do not control, will not have this log CP. So the question would be, can we see a black hole production by collider? This would be something like, I don't know if one. It was important. We use this enhancement property to isolate one contribution from the other, and in general, we don't know which contributions are really isolated, which are not. And one last comment, if I may, I forgot to, which is that maybe one of the basic questions for the boost in gravity and quantum gravity is the following: that we have the Regge intercept in the planar theory. It's less than 2, right? And in a non-planar theory, it's less than 1. And this was the source of all this enhancement and the amplitude. If I expand the exponent, it grows with f. If I exponentiate it, it's bounded by 1. So the question is, how do we go from here to here? And if you look at the gravitational loops, 1 loop or 2 loop on supergravity, people compute some of these things. You see that at every order in G Newton, you get G, this Regge intercept becomes worse and worse and worse. Full theory, it has to already sum this non-planar intercept. And you can use this model, simple model, to understand how this could happen. And basically what happened is that it seems like a better way to think about the correlator. You write it as the integral of the complex spin, and you get some G Newton, say, or 1 over CT to the power GL here. So, and you have some kernel. So if you want to recover the usual perturbation theory, you just close the spin contour and you recover the perturbation theory. But in a non-perturbative theory, this is a pure phase bounded by 1. So this ansatz seems to capture, and this is how you think of the iconalization. So it seems like this complex spins, the principal series for spins, would be important to, it seems like a very natural language to think about this problem. But this problem involves 2 things. First, unitarization of large impact parameters, which was done here, but also the scattering of 0 impact parameters has to be unitarized. And 0 impact parameter scattering is very UV sensitive. It's sensitive to the string scale or to whatever other scale. So it seems like the signatures of the unitarization of the small impact parameter physics are interesting. That's the basic point. And in fact, this kind of ansatz was discussed in a paper by Simon and Joshua Sander. And they had a paper about fishnet, and they have similar representation there.